In the world of AI, you always hear the same thing. More data is better. Just feed the machine more and more information, and it's going to get smarter. But what if I told you that sometimes adding more data can actually make your model dumber? I know, it sounds completely backward, but it's a super real problem that's been bugging data scientists for decades.
Okay, so let's start with what we all just assume is true. In machine learning, your gut tells you, give a model more features, more columns in your spreadsheet, and it's got to get smarter, right? More info should mean better predictions. It's the classic more is better way of thinking.
But this is where our intuition just hits a brick wall. See, researchers have noticed for a long time this really strange effect that turns that whole idea on its head, a point where adding perfectly good data starts to give you bad results.
Yep, this is what makes total sense to us. More features should create a clearer, more detailed picture for the AI. It just feels logical.
But then, this happens. As you feed in more and more features, your model's performance climbs, which is great, but only up to a point. And then, all of a sudden, it just takes a nosedive. This is the exact moment the so-called curse sinks its teeth in.
So this isn't just some weird fluke, It actually has a formal name. It's called the peaking phenomenon, or sometimes you'll hear it called the Hughes phenomenon. It's a well-documented, totally repeatable problem where a model's performance hits its peak and then starts that mysterious, super frustrating decline.
And look, this isn't just a story people tell. The research is totally clear on this. If you have a fixed amount of training data, you're going to hit a dimensional ceiling. And after that point, performance doesn't just flatline, it actually gets worse. So the billion-dollar question is, why? Why does this happen?
To really get the why, we have to take a little trip into the bizarre, kind of mind-bending world of high-dimensional geometry. And trust me, this is where things get really fascinating. The heart of the problem has this fancy name, distance concentration. But what it really means is that as you keep adding more dimensions, the data space just explodes. It gets so vast that every single data point basically becomes its own lonely island, super far away from all the others.
Now, this is what's so cool about this slide. It makes that abstract idea totally concrete. Think about a simple 2D space, like a flat map, right? The idea of a nearest neighbor actually means something. Points cluster together. But you jump into a 1,000-dimensional space, whoa. The very concept of near completely breaks down. The distance to your closest data point and your most distant one becomes pretty much identical. Everything is just far.
And you can see why that's a total nightmare for an AI. I mean, if every point is equally distant, how on earth is a model supposed to find patterns? Those nearest neighbor algorithms become totally useless. The model can't tell what's important, the signal, from all the junk, the noise. This is called swamping, and it's where a few really important features get completely drowned out by hundreds of irrelevant ones.
Okay, so if just piling on more features is a trap, what do? How do we escape the curse? Well, let's look at how data scientists actually turn this data overload into real insight.
It's not about finding some magic algorithm, it's about being smart. A good data miner's first step isn't to build a model, it's to just explore the data. They try to really understand what it represents and what the final goal is, and only after they get that deep understanding do they move on to the really crucial step, thoughtfully cutting down the number of dimensions.
And there's a whole toolkit for this. You've got feature selection, which is basically just intelligently kicking out irrelevant data. Then there's a really powerful technique called principal component analysis, or PCA, which is awesome. It combines related features into a smaller set of more powerful ones. And hey, even simple things like just removing the extreme outliers can make a huge difference.
But hang on, here's the final and kind of mind-bending twist in this whole story. What if this so-called curse wasn't a curse at all? What if for the most advanced AI models we have today, it's actually a blessing?
Yeah, because it turns out that some cutting-edge research is completely flipping the script. The newest generation of AI models are being designed not just to survive in these huge, high-dimensional spaces, but to actually use their weird properties to their advantage.
A perfect example is this technique called Matryoshka representation learning, or MRL. The name is just perfect. It trains a model to create data representations that are nested inside each other, just like a set of those Russian Matryoshka dolls. This gives the model amazing flexibility. It can use the full high-dimensional doll for a really complex task, or just grab the tiny, low-dimensional inner doll for a quick, simple one.
And the efficiency gains are just staggering.
On some tasks, an MRL model can get the exact same accuracy using a data representation that is up to 14 times smaller. That's not just an improvement, that's a revolutionary leap. And this is a great way to picture what's happening. On the left, you see all the noisy, messy features a standard network might pick up. But techniques like dropout, which was actually an inspiration for this work, force a network to find the clean, independent features you see on the right. MRL takes us to a whole new level, finding the perfectly sized, clean representation for any problem. It finds the real signal buried in all that high-dimensional noise. And this all leads us to the ultimate payoff, the blessing of dimensionality. This is the counterintuitive idea, that high-dimensional space is so incredibly vast that, if you're clever, you can find a way to arrange your data where complex patterns actually become simpler and easier to separate than they ever could be in a crowded, low-dimensional space. It's about turning that vastness from a problem into a massive opportunity.
So it leaves us with this final thought to chew on. We live in the era of big data, where we're always chasing more. But maybe the real challenge, the next great frontier for AI, isn't about how to get more data at all, but about mastering the subtle and powerful art of knowing what to ignore.